Wall power is alternating current. It pushes and pulls electrons back and forth 60 times a second. But your laptop, phone, and almost every modern electronic device require direct current, a flat, continuous, one-way flow of energy. To bridge that gap, we use a component called a diode. It acts as a one-way valve, letting electricity flow forward while completely blocking it from going backward. Today, we are going to open up a free circuit simulator and build a complete AC to DC power supply from scratch, using standard rectifier diodes and a specialized Zener diode. Moving these concepts into a working simulation lets you safely test and manipulate the exact same circuits powering the hardware on your desk. Step 1. Open your simulator's component library so we can select the first parts of the circuit. The secret to this one-way valve lies in the silicon. Through a process called doping, manufacturers create two distinct materials. P-type silicon is packed with positive holes, while N-type silicon is loaded with free-floating electrons. By fusing them together, you get a P-N junction. Right at the border, the electrons and holes cancel each other out, creating a dead zone called the depletion region that normally blocks the flow of electricity. When you apply a positive voltage to the P side, it pushes everything toward the middle, shrinking that dead zone until current can flow through. If the voltage reverses, it pulls the charges apart, widening the barrier and shutting the flow off completely. There are many variations of this component designed for specific jobs, but for our main power conversion, we need the standard rectifier diode shown at the top. Because it uses that PN junction to slam the door shut on any backward-flowing voltage, a standard silicon rectifier is the exact tool we need to start taming our alternating wall power. Go ahead and drag an AC power source and 4 standard rectifier diodes into your workspace. This schematic compares two approaches. The left circuit is a half-wave rectifier. It uses one diode, which completely blocks and wastes the entire negative half of the AC cycle. Now look at the circuit on the right. This bridge rectifier captures the full wave. To build it in your simulator, wire your 4 diodes together end-to-end in a closed diamond shape. When you eventually build this on a physical breadboard, pay close attention to orientation. The physical diode has a silver stripe indicating the negative end, which corresponds exactly to the vertical line on the schematic symbol. Wired in this diamond pattern, the circuit behaves like automatic traffic lights. No matter which direction the incoming AC wave pushes, 2 diodes will open and the other 2 will close, forcing the current to your device in a single continuous direction. We now have direct current, but the voltage is still pulsing up and down with every wave. To fix this, wire a Zener diode across the output lines, parallel to where the final load will go. This is the current voltage curve for a diode. Looking at the right side, you can see that a standard silicon diode needs to cross a threshold of about 0.7 volts before it lets current flow forward. Now look at the left side, the reverse breakdown region. Pushing a high backward voltage through a standard diode destroys it. A Zener diode, however, is manufactured to operate safely right here. By installing the Zener diode in reverse bias, we set a hard limit on the voltage. As long as the power is under that limit, the Zener ignores it. But the second a voltage spike hits, the diode activates and shunts the excess current safely away from your load. This deliberate reverse breakdown acts as an automatic pressure relief valve, clamping the final output into a steady, safe DC voltage. With the components in place, hit play on the simulator and attach virtual oscilloscopes to both the AC input and the final output. You'll see the chaotic AC sine wave on the input side, entering the bridge, transforming into a series of positive bumps, and finally smoothing out into a flat, steady DC line. Before we finish, we have to calculate our exact output power. This formula shows how to find the effective peak voltage coming out of a bridge rectifier. Because the current has to travel through 2 active diodes during every half cycle, and each diode consumes that 0.7 volt threshold we mentioned earlier, the circuit imposes a total penalty of 1.4 volts. So if you hook up a 12-volt AC source, you subtract the 1.4 volt drop, leaving you with an effective peak of 10.6 volts right before it hits the Zener regulator. Calculating this 1.4 volt loss ensures you provide enough raw input power to meet the precise requirements of your real-world electronics. We started with alternating power swinging violently back and forth, pushed it through semiconductors, and converted it into a steady, clean energy stream. Your simulator design is complete. The next step is to order the parts and wire this exact configuration onto a physical breadboard. As a final test in the simulator, try deleting the 4 standard silicon diodes and replacing them with Schottky diodes to see how a lower voltage threshold improves the overall efficiency of your bridge. Converting AC to DC is the prerequisite for modern technology. Mastering this circuit equips you with the exact knowledge needed to repair, troubleshoot, and build the power systems that keep the world running.